Ask a frontier model to call a specific tool, and two things consistently fail. It either invents an API that does not exist, or it botches the required arguments for one that does. This breaks down further in production environments. The real web relies on thousands of overlapping APIs that constantly update their versions. You cannot simply paste the manuals in as a prompt. The sheer volume of this documentation far exceeds the context window limits of standard retrieval-augmented generation. Fixing this behavior requires a different approach. Reliable tool use is a problem of structural formatting and data routing, not simply scaling up parameter counts. In 2023, a research group proposed a fix called Gorilla, an open-source model with just 7 billion parameters. Developed by a team at UC Berkeley in a close collaboration with the team at Microsoft Research. Despite its smaller size, Gorilla surpasses GPT-4 at writing API calls. The mechanism driving this performance is harness engineering rather than novel neural architectures. This pipeline relies on three specific interventions: synthetic data generation from existing documentation, a retrieve-aware prompt format, and a structural evaluation metric to score outputs. By examining these three components, we can understand exactly how a 7 billion parameter model outperforms a much larger system at specialized tool execution. Training a model to call tools requires a baseline dataset of accurate API usage. The researchers built API Bench by scraping these three hubs to yield 1,645 machine learning APIs. Each API is normalized into a model card JSON, where the critical API call field provides a clean, machine-readable route for execution. To fine-tune a model, you need instruction-to-action pairs. Manually writing thousands of these examples is the primary bottleneck in tool use training. They bypassed this using a process called self-instruct. Seeded with 18 handmade examples, they prompted GPT-4 to generate 10 distinct, realistic user instructions for every single API document. The strict constraint here is that the generated instructions are forbidden from naming the API itself. While GPT-4 generated this data, the researchers note it is interchangeable with other open-source models. The scaling method is the breakthrough, not the specific text generator. By withholding the exact API names in the training instructions, the model is forced to map the user's underlying intent to the correct action, rather than relying on keyword memorization. With 16,450 synthetic pairs generated, the team ran a standard instruction fine-tune on a base LLaMA 7B model. The key intervention occurs during this training phase, utilizing a technique called retrieve-aware fine-tuning. During training, the system constructs a prompt string where the retrieved API document is prepended directly alongside the user's instruction. This mathematical shift teaches the model to process both the document and the query to construct the final call. This prompt format gives the model test time adaptability when documentation inevitably changes. For example, an API might update from ResNet 50 to 101, or switch its repository entirely. Because the model is trained to read the appended document first, you can swap in the updated documentation at runtime, and the model adjusts its output accordingly without requiring a new round of training. Retrieve-aware fine-tuning shifts the system from a static catalog of memorized calls into a functional parser of real-time documentation. Once the model outputs a call, we need an objective way to determine if it is actually correct. Standard software unit tests do not work well for this. An instruction like classify an image can be fulfilled by dozens of valid models, making a simple pass or fail result highly ambiguous. Gorilla maps outputs to an abstract syntax tree. A call is scored correct if its root node and declared arguments match an API in the database. It explicitly ignores optional leaf arguments, so flipping a flag like pre-trained does not register as a failure. This structural comparison yields a specific trichotomy of results. First is a clean correct, where the subtree matches perfectly. Second is an error. This happens when the model successfully targets a real database API root, but invokes it with the wrong required arguments. The third outcome operationally defines a hallucination, a generated call whose root node appears in no database API at all. AST matching takes the vague concept of a model hallucinating and grounds it. An entirely imagined tool becomes a mathematically detectable property that a script can decide instantly. Evaluating the fine-tuned 7 billion parameter model against existing frontiers reveals a clear divergence in accuracy. Looking at this summary of zero-shot results, Gorilla outperforms GPT-4 across the TorchHub, TensorHub, and Hugging Face datasets by over 20%. Simultaneously, the AST metric confirmed that hallucination rates dropped into the single digits. The most informative element is this retrieval ablation chart, tracking performance across search algorithms. With a perfect Oracle retriever, the retrieve-aware model hits massive accuracy ceilings. But with real-world systems like BM25 or GPT Index, performance drops well below that maximum. The researchers conclude this bluntly. Given current technology, fine-tuning produces better operational results than retrieval. The primary constraint preventing highly accurate tool execution is no longer the reasoning capability of the language model itself, but the precision of the external document retriever feeding it. It is necessary to contextualize these findings within the specific limitations set by the study. The system was tested exclusively on linear, single-call machine learning APIs, rather than complex chains of multi-step agent actions. Furthermore, the Hugging Face benchmark relied on an asymmetric multiple-choice evaluation, and the entire test dataset shares its lineage with the same GPT-4 process used for training. Despite constraints, Gorilla is the textbook example of internalizing data through fine-tuning, demonstrating how to bake structural logic directly into a network's weights. Connecting language models to massive real-world toolsets does not strictly require scaling models to increasingly massive parameter counts. Reliable API execution is achievable through rigorous formatting, highly structured prompt engineering, and precise mathematical definitions for failure.